Hello, this is our heat transfer project, and the members are Fernando Rivera, Abdel Gutierrez, Julio Garcia, and Jaime Hernandez. For the introduction, we have wrote that electronics have led to the technological advances in the past years. The recent increase in processing demand has forced manufacturers to increase the performance and functionality of integrated circuits, chips, and minimize their size, leading to high power dissipation through smaller packages. This has made thermal management a critical aspect of successful processor systems design, and finding new cooling techniques has become much more valuable. Moreover, the failure rate of electronic systems increases exponentially with temperature. The operation of electronics produces leakage power and degrades the reliability of integrated circuits. Integrated circuits packages must be designed to remove predicted excessive heat to avoid leakage in order to reduce the temperature of chips and consequently avoid any potential failure. Active and passive cooling techniques are used. In many applications, standard cooling methods are inefficient for the heat loads produced during continuous operations over long periods of time due to the limitations such as limited thermal conductivity of air for convection and copper for conduction, and small spaces decreasing the performance. This project will discuss the test and thermal properties of an aluminum heatsink simulation. The intent is to cool the heatsink base from 85 degrees Celsius to 65 degrees Celsius using natural convection. In order to simulate surface temperatures acting on a surface board, the project will be used an aluminum plate, and the initial area of the aluminum plate given for this experiment is 7.62 by 2.4 centimeters. The goal is to design a plate that dissipates the heat effectively and efficiently. For the theoretical background, we wrote that as they need to efficiently and effectively cool down computer processors as they improve with increased performance, their smaller size can quickly increase the temperature as they consume more power with tasks that require more processing. An example would be how Intel processors can reach temperatures of over 90 degrees Celsius under an intensive load. And using heat sinks can help dissipate the heat away from the CPU, decreasing the temperature due to the fins in the hot plate. The sink will draw heat from the base into the surrounding environment through the fins. Fin surfaces are made from a highly conductive material such as aluminum, and increasing the surface area of the fins can increase the heat transfer by exposing the area to convection and radiation. When analyzing fins, we consider a steady operation with no heat generation and constant thermal conductivity for the entire surface of the fin. Using the fin equation, we can consider the volume of the fin at location X, and having a length of delta X and cross-sectional area AC with a perimeter of P, the thermal energy balance ratio is expressed as the rate of heat conduction into element X, which equals the rate of heat conduction from the element at X plus delta X plus the rate of heat transfer convection from the element. As fins are used to enhance heat transfer, the fins cannot be recommended unless the heat transfer can justify the complexity and cost associations with the fins. There is no sure way of knowing if adding fins into the surface will enhance heat transfer without the proper equation, but the performance on how well the fin performs is expressed with the fin effectiveness E-fin equation, which is E equals Q fin slash Q no fin, where Q no fin is equal to HAB parentheses TB over T infinity. And effectiveness of how one shows the addition of the fins does not affect the heat transfer. The heat conducted to the fins into the base area, AB, equals the heat transferred from the same area to the surroundings. Effectiveness less than 1 shows the fins acting as an insulator. When the effectiveness is more significant than 1, the heat enhances the heat transferred from the surface. For this project, though, the fins will transfer heat through the natural convection, and natural convection occurs when any fluid motion occurs naturally, such as buoyancy. In contrast, forced convection uses a pump or fan to increase heat transfer.
Our group decided to go for a very well-known heatsink known as the extruded heatsink. The heatsink extrusion has many benefits that consist of having high efficiency, economical, and it can vary between different shapes and sizes. This benefits the sink by having good thermal conductivity and a fast heat dissipation. It weighs less compared to other heatsinks, which makes it easier to move or install. The heatsink is 13-fin aluminum block with a length of 76 millimeters.
Each fin has a thickness of 1 millimeter.
Fusion 360 was used for the temperature where the CPU should drop from 20 Celsius from the original temperature of 85. Right here you can see the actual Fusion design that we came up with. This is the up view, this is a side view, and this is a 3D view. Down here, we made a couple of variations for renderings of the Fusion design to show how the fin would look in real life.
Okay, for the equations, we use these 4 equations, which Q, the most broad equation in heat transfer. The Rayleigh equation, the Nusselt equation for the Nusselt numbers, and the Nusselt output for the number. So we got a couple parameters for the heatsink itself, where T infinity is 25, and all this Q, K, PR, and T film were gotten from the table A15. And our assumptions were one-dimensional natural convection. Since we have no external force or forced air, heat transfer coefficient K is not constant, and thermal conductivity K is constant. And here, the Rayleigh number, we just substituted the numbers that we have, which most of them were from the table and from the assumption. The only one that we did not have was H, and we solved here by getting the Nusselt number. And here we just give the number of fins, that way we can submit it to our final equation.
For the methods, the temperature decrease shown in the simulation using Fusion 360 was 11 Celsius. As shown in the calculations, the goal is to decrease the temperature from 85 to 65. Using the equations found in chapter 3 and 9 of Sego heat and mass transfer, we find that dissipation is the 13 fin heat sink. A set of equations was used to calculate the heat transfer rate throughout the sink. A design replica was created in Fusion 360 and put through a series of simulations. The physical heatsink was machined using a milling machine and profiler. Results: the first simulation cooled the heatsink from 85 to 75 with a deficit of 9.25 Celsius. The heat reduction does not meet the standards to which the heat must be cooled. The following simulation reduces the heat from 85 to 68.32 Celsius with a deficit of 16.68 Celsius. Although the heatsink reduction is closer to the standard 22 Celsius, it definitely meets the requirements set for the project. The simulation did meet the same reduction as our calculations did at 20 Celsius for the 85 to 65. For the discussion, after performing multiple simulations and experiments, some calculations can be outlined. An increase in heat flux leads to an increase of steady state temperature. PSM contributes to delaying the peak of temperature by absorbing the heat, which leads to better long-term performance of the determinant uses of the chip. A variety of choices exist when choosing the appropriate PSM to be used in the application, but the decision depends on some properties: heat capacity, temperature density, and thermal conductivity. With the increase of density, the mass would change with the same volume, leading to the delay of the steady state temperature, and by increasing the thermal conductivity, the PSM would absorb more energy and melt faster during the heating process. For the conclusion, the paper is aiming towards simulating the heat distribution over a heatsink using Fusion 360 simulation, conducting, and its effect on peak time. In this project, the team aimed to compare theoretical and experimental values of a designed heatsink for a circuit board or CPU and determine the similarities of mentioned results. We designed and performed the thermal simulations of Fusion 360 of natural convection cooled heatsink with 13 fins that decrease the heater's temperature, circuit's board CPU by 22 plus, to simulate the heat distribution over the heatsink of 1 degree Celsius. This is accomplished by simultaneously by having the mass of the heatsink as small as possible, which is an essential factor given how compact said components are, and based on our simulation without outside matters.
And that completes our heat transfer project.
Thank you.